Alter, ich bin da seit 2 Jahren dran. So basically, device tree works like this. So this is the copy that the Linux kernel has made. Ich Salty oder Frank? So device tree works like this. You can see that there are a lot of things starting with a name and a comma. So for example, IBM secure boot is for their secure boot implementation, and IBM Opal is their open platform something. And there are a few things that are standardized. For example, and these don't have a comma. For example, there is a CPUs node where you say, okay, below there's all the CPUs. And yeah, there's also things like interrupt controllers and everything, but all of these are non-standard. Or only somewhat standard. So the basic idea is these names are like this is a Talos 2. So these names are basically like the PCI IDs. So drivers will match against these names. And usually you don't only have you have the name. Yeah, so each node has a name and a compatible. The name might be empty even, because bullshit. And compatible is a list of so this is a list separated by null bytes of devices this device is compatible with. So we are implementing the IBM Power NV spec. So if you have a standard driver for that, just use that. We also implement the Power 9 OpenBMC standard. If you have a driver for that, maybe that will help. And if all of that fails, then maybe use a standardized driver. Use a special driver. Yeah, that's for the full set. If you only get the main board, I like it when spammers are already automatically tagged for ban evasion. Makes my life so much easier. So yeah, that's the full machine with sturdy case and everything. So if you just get just the main board and CPUs, it's a lot cheaper, and also it used to be a lot cheaper in the beginning. So I have paid a lot less than that, to put it mildly. So yeah, so basically you have this fallback list of possible drivers, and basically all the kernel has to do is go through the list of available drivers and match it against the names it finds here, and that's it. Or rather, match it against the compatible things it finds. and only for nodes it understands. So so a few things are fairly obvious, like okay, there's for example the memory nodes. There's memory at 0 and memory at long number. So this is on one socket, this is on the other probably. So the device type is fairly obvious. This is memory. It also has a name. This is obvious, that's memory. So if you look into the device tree and you see memory, then it says, then you know you found the main memory. And that one doesn't even need a compatible list because it doesn't need a driver. It's just fine. And one thing it also has is this reg thing. That in this case is 16 bytes, and that's always a number of cells for the start address and a number of cells for the size. How many is defined on the layer above. So if you go one layer out, here is a number of address cells. That says 2. And there's also a number of size cells, that's also 2. So with this, I know that I'm going to use 2 cells for the address. So one cell is 32 bits, so 64 bits for the address, 64 bits for the size. If I had more memory blocks, then this list would be longer. This and so this is obviously at this start address with this size. And oh, Debian Unstable läuft stabil. Verdammt. Nicht mal das können sie. And you can fairly easy go through the entire device tree and find all the mainboard devices this way. So there is a PCIe thing, or multiple even. These will have a name. That's a fairly standard thing. And they will have a compatible list, which says, okay, this is the PCIe X from IBM inside the Power 9. And it's also compatible with they just reuse this thing, and it's compatible enough that you can just reuse the old driver. Yeah, it's fairly okay to be 48 bytes. The number of size address cells and the number of size cells tells you how to interpret it. So if you have a 64-bit machine, then usually these two will be 2. Which means that you have 64 bits address, 64-bit size, and then if you have more, then you have more memory blocks. So you have three blocks of memory, for example. So, and the next thing they do is they have ranges. Ranges are, you can see it's a weird size. So, on this node, which is not the root node, you also have address cells, which in this case is 3. and size cells, which is 2. And ranges say this thing is a bus bridge. So anything that has a ranges property, this is a somewhat transparent bus bridge, or possibly transparent if the driver says it is. And we map this. Hold on. I think it's the outside addresses first. It has one folder, or one node, basically for every controller that should be on the main board. So what they are doing is this creates the mapping and says, okay, we have weird PCI addresses, and that have 3 numbers. Which is, I think it is domain bus device or something. Yeah, I think this is, yeah. So the inside address is first. So this is the first address cell of the PCI bus. This is the second. This is the third. This is the outside address of the bus, and this is the size which uses the size cells from the inside. So it says at this address there is the PCI Express bus mapped with that uses the PCI Express domain 2. So here domain 2 that is mapped to this address, and yeah, that one then has a PCI below it and so on. And the really interesting stuff is there's also there should also be things like SPI and other things in there. I'm not sure where they are connected. This looks. Yeah, and you can express other buses, like SPI or I2C or so below that. And so, for example, if you have an SPI bus on your main board and you have some device connected to it, then you would expose it in the device tree already, and the system can just find it. And since SPI devices are fairly standard, you wouldn't use your own driver for it. You would just say, okay, this is this standard device I bought from whatever, and it would just work. And all your driver has to do is like, I'm basically expecting 2 ADCs below my device node. Are they there? And then Linux says, yes, they are here, and then you can just use them. And if you know how to do this properly, then you can write a device tree that you never have to change again. And well, like 80% of your devices are supported from the beginning, and everything else can be just and anything else will not conflict with any existing driver. Yeah, and there's a few special nodes. For example, there's the chosen nodes that has the boot arcs and the handover for the init ramfs and stuff like that. The chosen node is basically what the bootloader has to fill out. Yeah, if you do it properly, you can get away with a lot of things. And if you ever have to pass a device tree from, if you ever have to load a device tree from the disk, then your firmware is broken, and somebody and everyone who uses it needs to work around your broken firmware. Chosen might have frame buffer. Chosen is basically free for all. There might be something like Linux, frame buffer or something like that. If you have a frame buffer that's already set up, that's way possible. And there's also, yeah, like things like, okay, we have a sale console and you should use it. And usually you don't have PCI devices themselves in there. You only have the root node. Because anything connected to the PCI bus can be scanned via PCI. You only add things you cannot scan. Yeah, and my expectation for anyone selling embedded systems would be that they ship a proper device tree that never has to be changed again. If they don't know what they're doing, then they should just use their own name and a comma in the compatible and just provide lots of drivers. That will suck, but at least it's conflict free. If they know what they're doing, they can save themselves a lot of work and just say, oh, the driver for this device already exists. We are just saying, okay, we are going to use it. I mean, when we did a CellBE mainboard, if the display changes, oh, you mean in a way that cannot be detected? I mean, normally, pretty much all of the embedded display solutions I've seen so far were you add an I2C bus and you add an EDID and just connect it. And your device tree says there is an I2C bus here, and the EDID is connected to that. You can also, if you like, embed the EDID in there, but nobody does it. I2C is only for monitor detection. Like you would detect it like you would do the normal monitor detection on a VGA or HDMI cable. All of this has been the same since the 90s. No, not like USB. It's like on a normal display cable. Every display cable has an I2C bus, and that's how you get the supported resolutions out of a monitor. And pretty much any embedded display solution I've seen has just used the same. And they're just saying, okay, we have an I2C bus. Yeah. Yeah, if they have to set up things, then either they have delivered a horrible hack, or they should do it properly. Or they should properly. Like, I mean, I don't have anything here with a device. Yeah, they built a horrible hack, probably. They're not supposed to be sell horrible hacks and expect everyone else to spend lots of money and time working around their horrible hacks. Easy as that. I have no idea what I just did. This is what happens if you throw around your screwdriver, which you've put away half an hour ago because you were playing around with it. So So 5 of